When we hear the word ancient, it's incredibly easy to just default to thinking primitive, right? We tend to imagine rough tools, super simple melodies, and basic trial and error craftsmanship. But what if I told you that some of the absolute oldest musical traditions in the world were actually built on a foundation of highly sophisticated acoustic engineering? Welcome to this explainer. Today we're going to explore how traditional Indian musical instruments aren't just beautiful works of art, though they certainly are. They are literal feats of physics. We're talking about instruments designed by artisans who fully mastered the science of sound centuries before the mathematical equations even existed.
Okay, let's dive right into this, because this quote perfectly captures the absolute mind-bending reality of what we're looking at today. It references a settled, fundamental rule of acoustics. Standard, circular drums simply cannot produce a clear harmonic pitch. They just can't do it. But Indian drum makers somehow completely hacked this complex physics problem. They created drums that literally sing, and they did it long before the complex mathematical formulas, like Bessel functions, were even conceptualized. So how on earth did they do it, and what other physical laws did these ancient artisans manage to master? Here is our roadmap for the explainer today. We'll start with the Nāṭya Śāstra framework, then cover strings for bending the pitch, winds for aerodynamics, drums for that impossible harmonic, solids for clay resonance, and wrap it all up with the universal symphony.
Section 1. The Nāṭya Śāstra framework.
Now, the Nāṭya Śāstra is this foundational Sanskrit text dating back over 2,000 years. And what's brilliant about it is how it categorized instruments purely by their physical sound-producing mechanisms. A really great example of this ancient terminology in action is the word Veena. Today, if you know Indian music, you probably associate that word with a specific beautiful instrument. But in the earliest Vedic texts, we're talking over 3,000 years ago, Veena was actually just a broad catch-all category for any plucked string instrument. In fact, there was even this legendary instrument called the Akasa Veena, which was essentially strings tied between treetops, literally designed to be played by the wind itself. But as you'll see, as these instruments evolved, the engineering behind them got incredibly precise. Section 2. Strings, or tatavadya, bending the pitch. So in this family, sound is obviously generated by a vibrating string under tension. But the way Indian instruments manipulate that vibration, it is uniquely fascinating. Think about a Western instrument like a piano. You move in discrete, rigid jumps, right? You press a key, a hammer strikes a specific string, and boom, you get a fixed note. But Indian classical music requires what are called gamakas, these highly ornamental, continuous slides between notes. On fretted instruments like the Saraswati Veena, or fretless ones like the sarod, and even the simpler ektara, the player alters the effective tension of the string in real time. They do this by physically pulling it sideways or sliding their fingers along it. So they are continuously manipulating the mathematical variables of the string's frequency, bending the pitch all over the place without ever breaking the sound. And this brilliantly illustrates that continuous acoustic control. But honestly, string physics gets even wilder when we look at the tambura. Now, this instrument doesn't play a melody at all. Instead, it provides this continuous, hypnotic drone in the background. It features a wide, very gently curved bridge called a jawari. Here's the crazy part. Artisans meticulously insert a tiny, tiny cotton thread right between the string and this curved bridge. Because the string grazes the curve of the bridge, rather than just stopping at a hard, sharp point, it creates something called resonant coupling. It generates this rich, constantly shifting spectrum of harmonics, a continuous, complex shimmer, instead of just a tone that slowly fades away. This acoustic phenomenon was actually so captivating that a young physicist named C.V. Raman, who, by the way, would later win a Nobel Prize, published a deep mathematical study entirely on this instrument way back in 1921.
Section 3. Winds, or Sushuravadya, aerodynamics and impedance.
Now, what's really interesting about this family is that the instrument's body doesn't actually vibrate. A column of air inside a tube is doing all the heavy lifting. The exact mechanism of how a player's breath becomes music is called an edge tone. When a player blows across the sharp blowhole of a simple bamboo bansuri flute, they aren't just whistling into a stick. They are deliberately creating an oscillating air jet instability. The air rapidly deflects in and out of the tube, creating a feedback loop that pumps acoustic energy directly into the air column inside the bamboo. By covering or uncovering those little holes, the player is instantly changing the effective length of that air column, perfectly calculating the resonance to change the pitch on the fly. But while flutes rely on those edge tones, reed instruments use pure pressure. Meet the Nāṭya. It's a massive double-reed wind instrument deeply rooted in South Indian temple traditions. The player's breath actually forces two thin blades of cane to snap open and closed incredibly fast, essentially acting as a rapid pressure-controlled valve. But what makes the Nāṭya truly legendary isn't just the reed. It's its sheer, overwhelming volume. Literally, you can hear this thing from incredibly far away. So how does an acoustic, totally unamplified piece of carved wood get so loud? Well, the secret lies in the instrument's massive flaring bell. This wide flare acts as an impedance-matching horn. Think of it as an acoustic bridge. It connects the high-pressure, narrow air column inside the instrument with the low-pressure open air outside. Without this specific flare, most of the sound energy would just hit the end of the tube and reflect right back inside. But because of this precise conical design, the acoustic energy transfers outward with maximum efficiency. It's literally the exact same acoustic engineering physics used in modern stadium horn loudspeakers, but it was perfected by temple craftsmen centuries ago. Section 4. Drums, or Avanadada Vadya, the impossible harmonic.
Okay, this brings us to the climax of our explainer today, and frankly, one of the greatest acoustic mysteries in all of musical history. I want you to really think about this question for a second. How do you make a flat, circular drum sing a specific, tuned musical note? If you hit a standard circular drum, like a Western timpani or a tom-tom, it doesn't really give you a clear, singable melody, right? It just gives you a thud.
So the crucial point here is that this thud isn't just a design flaw, it is a settled rule of physics. Because of a phenomenon called Bessel mode inharmonicity, the overtones of a vibrating circular membrane naturally fall at irregular, non-integer ratios. The math literally dictates that a plain stretched skin cannot naturally produce a clear, harmonic pitch. It's impossible. And yet, Indian classical drums, like the South Indian mridangam and the North Indian tabla, absolutely sing. They produce crystal clear, harmonic notes. So how on earth did Indian drum makers break a settled rule of physics?
Well, the answer lies in a meticulous, highly ritualized physical process. Drum makers take a super dense, heavy paste made of iron oxide. It's known as syahi for the tabla or karanai for the mridangam. They carefully apply this black paste to the exact center of the drumhead. But here is the genius part. They don't just smear it on willy-nilly. They carefully grade the thickness. It is perfectly thickest at the very center, and it thins out flawlessly toward the edge. By loading the center of the drumhead with this extremely specific mass density, they artificially alter the vibration frequencies. They literally force those messy, inharmonic overtones into perfect, integer-based harmonic alignment. It was such an unbelievable feat of acoustic engineering that the modern scientific community couldn't even explain how it worked until the year 1934. That was the year our old friend, the physicist C.V. Raman, finally published the mathematical proof that analyzed the syahi paste, validating exactly how this ancient technique perfectly corrects the drum's Bessel mode acoustics. Let's map this out and see how this builds, because when you look at the history, a massive gap emerges. We actually see double-headed drums in temple sculptures going as far back as 200 BCE. We see the modern tabla taking its shape in the 18th century, and then we have 1934 CE when modern mathematics finally catches up. This highlights a staggering historical gap between ancient artisanal intuition and modern mathematical validation. These instrument makers didn't have computer models, right? They had their ears, their hands, and a profound intuitive grasp of physics. Section 5. Solids or Ganavaja. Resonance in clay. Let's ground ourselves back into the earth for our final family, the self-sounding instruments, where the material itself vibrates. And there is absolutely no greater example of this than the khatam. At first glance, you might think, that's just an everyday clay water pot. But in South Indian Carnatic classical music, it has been elevated to the status of a virtuoso percussion instrument. The clay is uniquely fired to achieve a very specific tension and tone, and it's played incredibly rapidly with the palms, fingers, and wrists. But the true acoustic magic happens when the player presses the open mouth of that clay pot directly against their bare stomach while playing. By partially closing that opening in real time, the player actively alters the volume of the enclosed air cavity. This is an absolute masterclass in a physical phenomenon known as Helmholtz resonance. It's the exact same physics that makes a sound when you blow across the top of an empty glass bottle. By subtly manipulating that neck opening against their body, the khatam player dynamically shifts the pitch and resonance, pulling this deep, bass-heavy boom right out of a simple clay shell. It is amazing to watch. Section 6. Conclusion. The Universal Symphony. So when we look across these 4 families of the Nāṭya Śāstra framework, we've got the strings bending pitch in real time, flutes riding edge tone instabilities, massive temple horns transferring impedance, and those incredible drums that force harmonics through grated iron oxide paste. We see a truly profound truth. Art and physics are ultimately just 2 different languages describing the exact same universal truths. So I want to leave you with a final thought to chew on today. If these ancient artisans managed to master fluid dynamics, impedance matching, and vessel functions purely through intuitive craft, literally generations before the formulas were ever written down, what other modern scientific truths are currently just hiding in plain sight within our traditional arts? Thank you so much for joining me on this explainer. Keep listening closely and keep wondering.